Yeah, next up is backward elimination actually. Well, random subspace selection, as it is stated here, is actually 3.3 subspace projections. But anyway, so we'll talk about backward elimination in the next subsection. Maybe we go back a little bit here to see the big picture. We have these different search strategies, yeah, for the feature space. We talked about forward selection just recently, and now we're talking about backward selection. So we are not starting or looking at individual features and add relevant features and or dismiss irrelevant ones, but in that case we start with the entire data set, with the entire feature space, actually with the entire set of features, and then try to get rid of the worst ones, so to say, yeah, one by one. And we can do that this backward selection in also in a kind of branch and bound manner. Yeah, we can, but that in that case we need this monotonicity property for the subspace evaluation measure. Yeah, but we'll see that also in this subsection here. Yeah? So backward elimination can be done in a branch and bound fashion. We'll see that also right away. But in that case, we need a monotonic evaluation measure. If we don't have that, then we just have to do or employ other search heuristics. For example, a greedy best first search typically. Yeah, and we'll start with that actually. Yeah, so the general approach once again is in the backward elimination schema is we start with a complete feature space and delete redundant or irrelevant features. And we typically do that in a best first greedy way. So we generate all subspaces of the original feature space in the first step. All subspaces, that is a little bit fuzzy, that can be anything. But actually, if we start off with a d-dimensional feature space F, we generate all d-1 projections, yeah, all projections that whose dimensionality is one less than the one we started off. Yeah, so if D is the dimensionality of F, we generate all d-1 projections of this feature space F, and then we evaluate all these d-1 dimensional subspaces with a specific quality measure. Yeah, we talked about different quality measures before. And say R star here is the best one with respect to this quality measure, then if R star has the target dimensionality, meaning we still need to input as an input parameter the number of features that we want to get, the dimensionality of the resulting feature space, yeah, which should be smaller than the dimensionality of our original feature space, of course. Yeah. So if R star has the target dimensionality, we terminate. Else we just start the backward elimination with R star. So we go back to the first step and generate all d-2 dimensions in the second step, dimensional subspaces of R star in that case. Yeah, and so on and so on and so on. Yeah, so we start with the full dimensional feature space and then work through the set of possible subspace candidates by just reducing in each step of this greedy approach here. In each step we reduce the whole thing by one dimension, yeah, and then take from the resulting candidates the best one and work further with this candidate and still reducing by one dimension in the next step, and so on until we get the target dimensionality, which once again needs to be an input parameter. Yeah, that is obviously useful in both supervised and unsupervised settings, yeah, because we can employ any quality measure here. If we have a supervised setting, it could be a quality measure that takes into account the class labels. If not, we can measure structural characteristics and stuff like that. So that works in almost all settings, this kind of candidate generation or subspace generation actually. And what I just told you before, we can switch from a greedy search to a branch and bound method if the quality criterion is monotonic. What that actually means is, or we will talk about what that actually means on one of the next slides. Yeah. So if that is monotonic, then we can employ these branch and bound algorithms, which are very similar to the a priori style algorithms for frequent item set mining, which you probably know from KDM. Yeah? Okay, so that is the basic idea. So let's have a concrete look at one of the quality measures out there, which we want to introduce to you. That is a distance-based measure. So the idea here is that the subspace quality can be evaluated by looking at the distances, or taking the ratio between the distance between the within class nearest neighbor of all the objects and the between class nearest neighbors of all the objects. So what does that actually mean? Well, the distance to the within class nearest neighbor, that is denoted by the way here with this term here, is obviously the distance of any object O to the nearest neighbor having the same class label as O. Yeah? So CO is the class label, yeah? And we look for all the points that have the same class label as O, and the nearest neighbor of O in this set is or this determines actually, or this defines the nearest neighbor, the within class nearest neighbor distance of an object O. And analogously for the between class nearest neighbor, which is denoted by this term here of an object O, we look at all the objects that have a different class label than this of than the class label of O, and again take the nearest neighbor. Yeah? That is the distance to the between class nearest neighbor. Okay, that sounds similar, sounds reasonable. And then we take the ratio between those two, yeah, the between class nearest neighbor distance divided by the within class nearest neighbor distance, sum that up for all objects in the data set, and then just take the average of it. Yeah, so here the cardinality of S, that is a small mistake here on the slides here. You should be these cardinality. What is that, brackets or lines here around S. Yeah, so it's the cardinality of this the data set actually S. Yeah, so that is the normalized ratio between the within class nearest neighbor distance and the between class nearest neighbor distance. That's what is actually computed here. And obviously this is not monotonous, because deleting a dimension, we cannot say that the quality will increase or decrease. It can happen actually both. So there is no monotonous way. So monotonic would be if we delete one dimension in this subspace here R, then the quality criterion must increase or decrease or stay the same. That would be monotonic. That is obviously not the case here. Yeah, so this quality criterion may increase or decrease by deleting a dimension, so it's not monotonic. So we cannot employ branch and bound here. Yeah, and just as you see, beside distance-based, we can also work with the model-based quality measure. So here you directly employ the data mining algorithm. So that's actually a wrapper method. Yeah, so you employ the data mining algorithm to evaluate the subspace, for example, by just training the model that you want to use, for example, a Naive-based classifier. That is very often used, yeah, because we have to consider some practical aspects here in this case. Because well, first of all, the success of the data mining algorithm, so of the model that you apply here, must be measurable. For example, class accuracy, whatever. Yeah, so we need to have a measure about the performance of the model that is applied to evaluate the subspace. Otherwise, we can't evaluate it. Yeah, obviously. Yeah, so it needs to be measurable. Then the runtime for training and applying the classifier should be low, of course. Yeah. Otherwise, it takes a lot of time to, you know, if you go through all of these greedy backward elimination and have to, for all these subspace candidates, and there are quite a lot actually, for all those you need to actually, yeah, train the model and then apply the model in order to measure actually the success of this model, yeah, in the particular subspace. Then the classifier parameterization should also be not of great importance, because otherwise you need to somehow tune these hyperparameters, and that might be quite costly, as we got to know already in the introductory part. Yeah, so recall the things we got to know about hyperparameter tuning can be quite nasty and quite time consuming. So in that setting, it would be good that if we can just run the learning algorithm here, the data mining algorithm, with saying some kind of default parameters, and that is quite okay, because the algorithm is not too sensible to these parameters. Yeah. And last but not least, test sets should have a moderate number of instances, just because that has, of course, an impact on training and especially on testing. Yeah, so that is something we just have to take into account here.